Welcome back. So in our last section for chapter 4, we're going to put together everything that we've learned about working with exponential and logarithmic expressions and equations, and we're going to start solving some equations. Now, general rule of thumb in life as well as in math, always remember, work smarter, not harder. Choose the easiest method you can to solve. There's almost always more than one approach to a problem. If you can figure out the simplest and quickest version, you're more likely to get there without mistakes. So that's our goal. Now, in that theme, our one-to-one property, if you can use this is going to be the one to use. This property applies to both exponents and logarithms, and it's usually the easiest approach you can use. So keep that one-to-one property in your hip pocket. Make sure you pull it out whenever you can. If you're in exponential form, the rule is with one-to-one that if the bases are the same, then the exponents are equal. And this is super, super simple. For example, if I have 2 to the x plus 3 power is equal to 4, my bases are not the same. But I can rewrite 4 as 2 squared, right? 4 is 2 squared. So I can say, all right, this is the same thing as saying 2 to the x plus 3, no, that's right, equals 2 squared, because 4 is just 2 squared. Now my bases are the same. Bases are the same. That means that my exponents can be set equal to each other, and I can say that means that x plus 3 has to be equal to 2. Well, subtract, subtract, x is a -1. Super simple, done. Plug that in, -1 plus 3 is 2, 2 squared is 4. So if the bases are the same, then I can set the exponents equal to each other and finish solving. If I'm in log form, this was an exponential equation, if I have a log equation, if the bases are the same, then the arguments are equal. So in log form, let's say I have log base 2 of x equals log base 2 of 15. The bases are the same, so I can say, therefore, that x equals 15 because the arguments are equal to each other. The bases are the same, the exponents are equal when I have exponential form. If I'm in log form, if the bases are the same, the arguments are equal. All right. 4 quick vocabulary check things. This is my one-to-one property. The bases are the same, so we know that our exponents are equal. That's my one-to-one. Once again, the bases are the same, so I can say the exponents are equal to each other. Let's go ahead and finish solving this. Let's go over here and solve number 2. We've got 4x minus 1 equals 7. So 4x is equal to 8, which means x is equal to 2. If I come back over here and I check, 2 to the 4 times 2 minus 1, 4 times 2 is 8, 8 minus 1 is 7. 2 to the 7, that checks. All right, here we go. If x times natural log of 9 is equal to natural log of 20, then what is x equal to? This is super simple. It's just not even a property we were working with. If I have x times something and I want to solve for x, that means I can divide both sides. So x is natural log of 20 over natural log of 9. And natural log is one of my bases in my calculator. So you can plug that into your calculator. Make sure you use correct order of operations. Natural log 20. I can either hit enter or close my parentheses and do divided by natural log of 9. Let's round to 2 decimal places. So I have 1.36, about 1.36 for that one. All right, right here, let's see what we've got. We've got e to the 0.6x equals 6. Our x, our variable, is in our exponent, and this is our exponent. Well, I am using my definition of logarithm here. We use definition of logarithm a lot. Got my exponent. It's going to be equal to log base e. Well, log base e I need to write as natural log of my argument. So right there, I've got exponent equals natural log of my argument. Natural log, I could finish solving, couldn't I? Solving for x, I divide both sides by 0.6. So let's do that. Let's do natural log of 6. And then I need to divide that by 0.6 to finish solving. And round to the 2 decimal places, that would be 2.99 when I round correctly. About 2.99. Excellent. Okay. So now we're we've got some more 5 through 7. Let's keep going. We've got log base 5 of x plus 1 equals 3. X plus 1 is my argument. The argument is equal to, let's put this in log form. We're using our definition of log again. If we're solving for x, x is in the argument, we've got to get it out of the argument. The way we do that is to rewrite it in exponential form by using definition of logarithm. So here's my argument. I've got log, this is log form. I don't want to keep it in log form. Good grief. Excuse me. That's my argument. My base is 5. My exponent is 3. So I use definition of log. Base is 5. Exponent is 3. Equals the argument. What is 5 cubed? Well, 5 cubed is 125. So I've got x plus 1 equals 125. And then subtract 1 to finish solving. I get that x would be 124. Alright, take a look at number 6. See what you can do with it. I see that I've got 2 log statements, base 3, and I'm adding addition pairs with multiplication. So this is my product rule. Log base 3 of, and I have in my argument x times x plus 1. I multiply those arguments together is equal to 2. Let's go ahead and finish working on this. Log base 3 of x squared plus x is equal to 2. My variable is in the argument. I've got to get my variable out of the argument to solve, so I'm going to use my definition of logarithm. Base is 3, exponent is 2, equal to the argument, and I need to finish solving. Well, 3 squared is 9. And now this is squared, quadratic. I want to see if I can factor it. The squared term is positive, so let's move that 9 over so that we have 0 equals x squared plus x minus 9. You know what? That's not factorable. It's quadratic, it's not factorable, so what would I do with that? Probably I'm going to use my quadratic formula to solve. We don't want to focus on quadratic formula right now, so we're going to stop there. We've got potentially two. We would have to check it against our argument, but we've got potentially 2 solutions. We have to make sure that our argument stays positive. Alright, let's look at number 7. See what we've got going on here. Natural logs are equal to each other. Oh, 1-to-1 property. 1-to-1 property is easy. Natural log base e equals natural log base e. If the bases are the same, then the arguments are equal. I like 1-to-1 property. Alright, so let's see what we can do about this, about solving. I need to get this x plus 1 out of my denominator, so I'm going to multiply both sides by x plus 1. Anything over itself is 1. So this leaves me with 7x minus 23 equals, and I need to FOIL this. X squared plus x minus 3x is a negative 2x. Negative 3 times 1 is negative 3. Again, it's quadratic, so I need to set it equal to 0 and try to factor. I'm going to subtract my 7x. I'm going to add 23 to move it over. You have to do the opposite operation, remember. 0 equals x squared minus 9x plus 20. Let's see if this one's factorable. I think it's going to be. X times x is x squared. The signs are going to be the same, and they're both going to be negative. Factors of 20 that add to 9. Well, 1 times 20, 2 times 10, 4 times 5. Perfect. 4 times 5. And then to finish solving, we set each of those equal to 0. And we get proposed solutions positive 4 and positive 5. I want to go in and check and make sure that if I plug those in, my arguments will stay positive, and it looks like we're in good shape. So that's going to have 2 solutions. All right, excellent. Okay, solve each exponential expression by using the one-to-one property. So we've got more practice on our one-to-one property here. Remember, one-to-one property, our goal is to start by making the bases the same. So base 2 to the x equals 2 to the something. How many times do I multiply 2 together to get 64? Hopefully we've done 2 to powers enough that you have a good idea and you can start playing with it and working with your calculator. 2 times 2 times 2 until you figure out that 2 to the 6th is 64, which means since we're using the one-to-one property, the base is the same, which means my exponents are equal, and we're done. All right, let's look at the next one. We can't go bigger, so we're going to have to see if we can match that smaller base, base 5. 5 to what power gives me 125? Well, 5 squared is 25, 5 cubed is 125, and the one-to-one property tells me that if the bases are the same, the exponents are equal. And again, we're done. Can't go with the larger base, so let's see if we can write them both in terms of the smaller base. 2 to the something equals 32. Well, 2 to the 6th was 64, 2 to the 5th is 32. We've got the bases to match, which means my exponents are equal. So 2x minus 1 equals 5. This time I need to do a little more work. Finish solving for x. So I get that x is equal to 3. All right, I've got choices here. My first choice is to see if I can match the smaller base. If I can say 4 to the 2x minus 1 equals 4 to some power. Is there an exponent of 4 that gives me 64? Well, 4 times 4 is 64. No, 4 times 4 is 16. 16 times 4 is 64. So there is, and I can leave this base 4. You could also change them both to base 2 if you wanted to. Okay, so exponents are equal. 2x minus 1 equals 3. So x would be 2. All right, number 12. Now, 8 squared is 64, not 32, so I'm not going to be able to use 8 as my base. I know I can't use 32 as my base. They're both even, so let's see if we can do a base 2. I've already got an x up there. Well, 8 is 2 cubed, so that one's easy. 32, we said up here, is 2 to the 5th. So I have a 5 times that exponent that was already there, that x. Which means that 5x equals 3. And x, therefore, is 3x. Okay, let's look at 13. Excuse me. 9 squared is 81, not 27, so I can't use 9 as my base. 9 and 27 are both divisible by 3. 9 squared is, or 3 squared is 9. I already had an x in that exponent. 3 cubed is 27. So my bases are the same. My exponents, therefore, are equal. So x would be 3 halves. And our last one, we've got 1 over 27 here, but I'm confident that I can turn that into a 3. So I've got 3 to the 1 minus x equals 3 to some power. Well, I just discovered that 3 cubed is 27, So if I make that a negative exponent, that makes that a 1 over 27. So I made my bases both 3 here by using a negative exponent. Okay, my bases are the same, so my exponents are equal. If we'll just do it this way. Negative x equals negative 4. Divide both sides by negative 1, and I get that x is equal to 4. One-to-one property is my favorite. If you can make the bases match, those exponents are equal to each other, and it makes life super easy. Now, there are 4 basic methods for solving exponential and log equations. Here is our goal for this unit. 4 basic methods when we're solving exponential and log equations. Some are easier than others depending on the situation. Some take longer than others. We always want to use the easiest one that we can. What's easiest? Well, if I can use that one-to-one property, that's usually going to be the easiest approach. So I try that first. If I can't try that, I've got 3 other options. If there is more than one log statement, more than one log statement, more than one log, I'm going to use my definition of logarithm. Oh, I just looked at 2 different rows. Guys, back up with me. Pull out your white out. Get out your eraser pen. We're starting with if there is just one log statement. How about if there is just one log statement? Second one's going to be if there's more than one log statement. Look at that. One log statement, more than one log statement. If I've got one logarithm statement, I'm going to use my definition of logarithm. My definition of logarithm tells me that I can turn every logarithm into an exponential equation. So I'm going to convert that. I've got one log statement, solving for x. I'm going to convert. What's my base? Well, log, no base written. That's got to be base 10. The answer to the log is my exponent, and that's equal to the argument. All right, what is 10 to the 4th? Well, it's a 1 with 4 zeros. So 1, 2, 3, 4, 10,000 equals x minus 3. Simple, simple. To finish solving for x equals 10,003. And if I plug that in, my argument's still positive, so we're good. Okay, now, what if there is more than one log statement? Now we're in the right spot. More than one log statement. Well, in that case, I'm going to apply the rules for logarithms. What are my rules for logarithms? I have a product rule, quotient rule, and a power rule. Look back at that last section of guided notes to find those. Alright, right here on the left side of my equation, I have 2 log statements combined with addition. Addition pairs with multiplication, so I'm going to use my product rule. Log base 2 of x times x plus 2 gives me an argument of x squared plus 2x. X times x times 2. That's equal to log base 2 of 6x plus 1. Now I've got a single log statement on each side. They're both the same base. I can use my one-to-one property. One-to-one property says if the bases are the same, the arguments are equal. Now, quadratic, so I want to move everything over so that the square term stays positive. So I've got x squared minus 4x minus 1 equals 0. That's not factorable. I can look at it and see because their factors of 1 are just 1 and 1. When it's not factorable, what do? Well, I use the quadratic formula. So x equals negative b plus minus b squared minus 4 times A times C all over 2A. So that gives me 4 plus or minus square root of 16. Negative times a negative is a positive, all over 2. 16 plus 4 is 20. So I've got 4 plus or minus square root 20 over 2. Well, 20 is not a perfect square, but 20 is 4 times 5, right? 20 is 4 times 5, and 4 is a perfect square. So I can rewrite that as 2 square root 5, because square root of 4 is 2. 2 square root of 5 is the same thing. That's how we simplify 20. So that's over 2. I have plus minus. This 4 is also over 2, and I need to simplify both of those terms. 4 over 2 is 2. Plus or minus 2 over 2 is 1. Square root 5. There are my two solutions. Now I need this. Those are proposed solutions. I shouldn't have boxed it. These are proposed. I need to think about if they're both going to work, because remember our argument has to stay positive, and this little argument here is x. So I need to know, are both of these positive values? So I need to check those solutions. If x equals 2 plus square root 5, that's going to be positive, so that's not a problem. But what about if x equals 2 minus square root 5? Let's grab our calculator and do 2 minus second square, so square root of 5. That comes out to be a negative 2.23. So that's negative 0.23. If I plug that in, it's going to not work because it's outside my domain of my function. It's extraneous. So this is the only solution. That's my valid solution. Those are proposed, but the negative one is extraneous. Okay, that's what I do. If I can use the one-to-one property straight off the bat, use it. If I have one log statement, use definition of logarithm, rewrite it in exponential form. If I have more than one log statement, use my rules for logarithms, and then if I need to, or I can, use the one-to-one property. If there are two exponential statements with different bases, two exponential expressions with different bases, I can't use my one-to-one property. Like right here, base 7, base 5, can't make those match. My rule is to take the natural log of both sides. So here's how this works. I'm going to say, all right, I've got natural log of 7 to the x minus 4 equals natural log of 5 squared. Now that I'm in log form, I can use my rules for logarithms. My power rule allows me to take those exponents and write them out front as coefficient. So I've got x minus 4 times natural log 7 equals 2 times natural log of 5. I'm solving for x. I'm multiplying this times natural log of 7, so let's just divide both sides by that natural log 7. Anything over itself is just 1. So I've got x minus 4 equals 2 times natural log 5 over natural log 7. And then to finish solving, I need to add that 4 to both sides. So here's what that looks like. X equals 2 times natural log 5 over natural log 7 plus 4. Now I gotta pay attention to my order of operations. If I ask you for an exact answer, there it is. If I want to round it to 2 decimal places, I've got to plug it into my calculator. Order of operations matters. 2 times natural log 5, enter, divided by natural log 7, enter, plus 4. So I get approximately 5.65. So depending on what kind of answer you want, you get it either exact or an approximate answer.